Good afternoon. Welcome to today's session on collaborative research theme. And Professor Ashok would be speaking today on an interesting topic. So I will just read out our speaker's bio today. And this will be in the few words that he has provided on the internet. So I'm sorry. So uh, Balakrishnan Ashok has a PhD from University of Massachusetts Amherst. Uh, he worked as a postdoctoral fellow in Lawrence Institute of uh, Theoretical Physics, Leiden, the Netherlands, and at the Material Research Center, IISc Bangalore. Prior to joining IIIT Bangalore in 2012, he was an assistant professor in the Central University of Hyderabad since April 2007. His research interests are in complex systems, nonlinear dynamics, biomechanics, biology motivated problems, theoretical soft condensed matter, and polymer physics, and all those difficult subjects. So we welcome Ashok to please deliver his Samvaad talk. Thank you.
Yeah, thanks. Today we will talk on some work that we have done on predicting spatio-temporal evolution of ocean carbon sinks and effect you can and how you can use that to kind of predict climate both into the past as well as the future. And this is collaborative work done with Professor J. Balakrishnan of NIAS, Eros Sunny, who was BSMS integrated maths department student at IISc and subsequently at NIAS, and he's currently a graduate student in the maths department at University of Florida, Gainesville, and also with Professor Jürgen Kutz at the Potsdam Institute for Climate Change. Details of the work, of course, you can look up the paper for further details. Okay. So what are we going to deal with in today's talk? We are going to, first of all, see what ocean carbon sinks are, a bit about marine chemistry and carbon dioxide, how it comes into the picture, well, which is the main thing. What is the global thermohaline circulation or conveyor belt in the oceans? How do we model flows between the oceans? How do we incorporate temperature dependence into this flow? How do we account for climate change by means of the Keeling curve, which is a curve for the carbon dioxide measured in the atmosphere? How can we identify the crucial control parameters for the system? How do we see the spatio-temporal evolution of carbon dioxide in each ocean through the model that we make? How do we look at the stability of the system? And how can we get insight into paleoclimatic conditions several million years ago? And of course, in the future, what might happen? But that's, of course, a big question mark. Right. So when you talk of sinks, essentially, we are talking of the oceans, the soil, and the forests. What are sinks? Sinks are entities which absorb carbon dioxide. So you can have sources as well as sinks in the environment. And the oceans absorb up to around 25 to 26%. It's roughly a quarter of the carbon dioxide that's emitted into the atmosphere. And the presence of sinks kind of regulates the carbon dioxide in the atmosphere, prevents the atmosphere from overheating. Okay. Of course, that doesn't mean the ocean doesn't release carbon dioxide. You also have sources in the ocean. But predominantly, the ocean is a sink. So this is, we have something called the global carbon budget. And people who are very interested in making a profession out of climate change often refer to these things. It kind of estimates how much gigatons of carbon is released into the atmosphere by fossil carbon dioxide, change of land use. So when these coming down, the uptake things that are marked here, these are the things that are absorbed by the sinks. Okay. So when they say there's a budget imbalance of minus 0.4, it means there's an imbalance between how much is released into the atmosphere and how much is actually reabsorbed. So this, they make a big deal out of it, but I'm not going to look at this. This is just to give you an idea of what's the motivation behind this when people make policies on climate change. Because there's one school of thought which says climate change is a natural thing, it should anyway happen regardless of human intervention. The other school, of course, says human intervention is driving the whole thing. So I don't know which is which. I'm just interested in modeling how the carbon dioxide is being absorbed by the oceans. Because the oceans is a primary sink. So again, this is again from that global carbon budget paper by Friedlingstein and others. It's a standard work, so in case people are interested, it's several authors, too many to list. So you have 472 gigatons of carbon by, it's a cumulative number. So this was actually a movie, so I freezed it for 2021. The 472 GTC being emitted by fossil fuels and due to other land activities, 218. The land, the soil absorbs 220 gigatons of this, whereas the ocean sink absorbs a similar quantity, slightly less than 176. And the remaining what is left between what is released and what is absorbed goes into the atmosphere. This is just to give you an idea of the magnitude of numbers involved. So when you're modeling ocean carbon sinks, we are considering, we have to take into account the fact that carbon dioxide is being released into the atmosphere either naturally or by anthropogenic activities. We are not making a distinction between the two. We are just looking at the net number. And this is absorbed by various natural carbon sinks, which might be terrestrial or marine in the environment. And since oceans are the major sinks, as I said, this is what we're going to look at. And in the ocean, you have something called the global thermohaline circulation or the conveyor belt. This thing. This is being released into the atmosphere.
Yeah, so
yeah, it's a cumulative number. So if you were to look from what the movie shows from the beginning, this just rises. Right. So whether it's real or not, I don't know. But this is what is, whether it's actually what's happening, that's of course the moot point. But from what we can see, each year this keeps going up. Cumulative. Yeah, so I'm showing just the last thing on this last slide because it's a PDF file. I can't show the movie. Which one? Oh, I think they made a mistake. That's all. This minus this. This minus this, it's kind of. No. You see now the magnitudes of this 472 minus. Is it less? Okay, perhaps it's, what is it, 438? Yeah, you are right, probably. Maybe it's in the negative in this case, but the point is this will oscillate depending upon how things will go. In general, it's going to rise up.
was there a point that
Net sink in the sense that if you look up, if you look to the earlier millions of years back at least, I don't know about the anthropogenic thing, the Miocene era earlier, the beginning of the Miocene era and the early Cretaceous, you had, Earth was much warmer than what it is today. So you had more generation of carbon dioxide and the net system was a kind of was heating up. But because carbon dioxide gets absorbed every now and then due to various, we'll look at that. This goes up and down. You can't see, no one was there around that time, right? So you don't know for sure. So this is what is postulated from what is seen in the record. So, okay, geological record. Can I proceed? Right. So when we talk of the global thermohaline circulation or conveyor belt, this is essentially deep sea and surface currents that are transporting heat and salt, so thermo and haline, heat and salt, from one part of the oceans to the other. The red streams that you see are surface currents, and these are warmer currents, mostly driven by wind. The deep blue currents are deep sea currents, deep ocean currents, and colder currents. And in general, while the the warm currents are driven purely by winds and currents, the surface water flows, these are driven by density differences in density and salt. Okay. So when you talk of, so these together, heat and salinity, form the global thermohaline circulation and are an important factor in how carbon dioxide is sequestered in the oceans. Okay. So when we are going to model ocean carbon sinks, we'd like to know what is the average salinity and aqueous carbon dioxide content. That is how much carbon dioxide is dissolved in the ocean after it's absorbed. How does it change with time? How does rising atmospheric temperature affect this absorption? How do you identify carbon sinks and sources? Do they remain static or do they move around or change with time and space? How does freshwater flow? In this case, the Amazon acts as a critical climate change parameter. This point actually was a hunch that started out when we were modeling it, and it turned out to be a crucial thing. And how do you explain differences between paleoclimatic and current day ocean patterns? Broadly, these are the things we're going to look at. Now, the ocean is a very complicated system, and we are not aiming to model ocean dynamics. That should be clear right at the outset. Because if you look at it, the ocean comprises of 3 horizontal layers. The upper surface, which is of a depth of 100 meters, is susceptible to wind motion and other surface events. Below that, you have something called the pycnocline, this thing down up to a kilometer, where water density increases with depth. And further, you have the cold, dense bottom, several kilometers below, where there's no effect of surface phenomena whatsoever. And any events here are purely density driven. So temperature and salt content purely drive currents in this area. Okay. Now you'll wonder why the slide showed up. When I'm talking of chemostats and serendipity and hunches, this is because the way we have modeled our system is by means of thinking of it as a chemostat. What is a chemostat? A chemostat is a container like this, where you have some biological culture that's put in and that's fed with some medium, and then you see, and then it's kept at equilibrium. So that's why it's a chemostat. So there's a paper on coupled chemostats which came up for review one day, and it was a very particularly boring paper. So it had to be done. So independent of that, I was thinking of this carbon sink problem. How shall we model it? Then I thought, instead of thinking of it as a culture in the protein, why not think of each ocean as a box and then proceed? And fortunately, that worked out. So that's why it's serendipity. The right paper came for review at the right time. And even though it had got nothing to do with oceans. And of hunches, okay, this is with respect to the Amazon. What I was thinking was that the Amazon is probably a critical control parameter in this whole system. Can we prove it? Okay, that was how it all started off. But we'll see. Right. The river. Even though the Amazon rainforest system itself has got a crucial impact on carbon sink absorption, I'm just talking of the river. So this is the model we have made. We call it a 5-box model because we are thinking of the North Atlantic as a box, South Atlantic, Southern, Pacific, Indian Oceans as separate boxes. The red arrows are surface flows, so wind-driven. And the blue dotted lines are density-driven deep flows, which is why I'm not explicitly showing the arrows, because if there's a change in gradient, the flow can reverse. And when we are considering the density of water, it's a function of temperature and salinity. So you have some, not really. You have always the Gulf current moving in one direction. You always have Aguilar's current moving in one direction. Right. So the alpha term here is something called the thermal expansivity coefficient. Beta is the Halline contract coefficient. This is to do with salt, of course. T is the temperature, S is the salinity. So this is starting equation when you're looking at density. But we neglect one of these terms, as you will see. Okay, before proceeding further, we talked of a box model, right? Now, if I had been a professional oceanographer and all, the box model is apparently a standard thing in people who model oceans, except that they don't model it in this fashion. This is it was first done by Henry Stomel, a very great oceanographer who was at Woods Hole near Boston. He was the first one to say that streamlines in the ocean are kind of contracted on the western side due to the Coriolis force. So he modeled it by looking at a 2D box, and then the Coriolis force, the height, it came in as the height of the, let's say, the amplitude of pressure due to the change in Coriolis force was put by these contour lines. So it's an entirely different kind of, it's a different kind of box. So when our box is nothing to do with Stommel's box, but when you talk of a box model in oceanography, this is what they usually refer to. And Stommel, I'm putting him up here, even though it's got nothing directly related to us, because this is classic paper. And because this man is a great man in the sense that he didn't have a PhD, but he was a professor at Harvard, MIT, and then later at Woods Hole. And he's one of two instances I know of people, great people who didn't bother with a PhD. The other guy you might have heard of, Freeman Dyson at, I think, Cornell, and then later Princeton. They didn't have bothered about a PhD, but great people. And I think he supervised some PhD students. So anyway, so he has also written some very nice books. One is Science of the Seven Seas, on the Seven Seas, other on the Gulf Stream, one more on the Coriolis force, which I haven't put up. And there's something called Lost Islands, about how people put up non-existent islands on maps. And then they look for it and say, hey, where is it? So elementary mistakes. Okay, it's a very nice book. You should see it if you can get hold of it. Okay. So Stommel's box model is entirely distinct from the box model we are talking about. But he was first in the game, so you should know about it. So what we are doing is, we are talking of density-driven and surface flows. So we are denoting deep water flows, that is not the surface flows, through this fashion. That's the flow rate kappa aj, dependent times the difference in densities. So flow coming from, say, ocean J into ocean I, that's rho I minus rho J, divided by some average density of soil, of saline water. So if I plug in the thermohaline coefficient and the thermal expansivity term that was shown there, you can just get this straight away. And I'm assuming that temperature of deep waters is constant around 3 degrees, so I'm dropping out one term. Okay. All right, so these are the form of what I'm going to call the deep water flow rates. The other term that shows up is the surface currents, Qij, and I'm considering some specific major currents. There's several surface currents in the ocean. I'm considering only the equatorial currents which govern transport from the Pacific to the Indian Oceans, the Guyana and the Central South Equatorial currents from South to North Atlantic, the Agulhas current, which is from the Indian Ocean to the Southern Ocean, but that's also some flow into the South Atlantic. And there's something called South Atlantic current that goes from the Southern Ocean, that is the ocean around the Antarctic Ocean, to the South Atlantic Ocean. Okay. So these together contribute, and you can calculate how much flows are there essentially from these currents, because people put buoys and all in the ocean, and they kind of track how much water flows past. So these contribute these various amounts. The units SV is a non-standard one. It's a Sverdrup, named after a Norwegian oceanographer. That's 10 to power a million meter cube per second. And these transports, these surface currents, are predominantly wind-driven, nothing to do with density or anything. Okay. So we have deep currents, surface flows. What else? We have to consider the influx of fresh water from melting polar ice, both in the Arctic, and so BNA means it's going into the North Atlantic, and BSO means ice that's melting into the Southern Ocean. Now, ice can melt or it can refreeze. So in this case, we found that at least for some current years, it was Antarctic ice was building up, so this was a negative quantity. Then you have to take into account rainfall over the oceans, how much water evaporates. So the sum of these two, precipitation and evaporation over the oceans. And then the largest fluvial source, fluvial means from rivers, largest fluvial source of fresh water, which is the Amazon, that contributed a sizable amount. We're not considering the other rivers because the flow in the Amazon is more than equal to the sum of all the other contributions from all the other rivers. Okay, right. So now we are we have to set up equations which will take care of how the flow of water is changing, right? First, so we are interested in carbon dioxide and salinity. So first, the change in salinity with respect to time. So you have all these terms from the various rivers. So when I say J, so this is influx and outflow. So that's why there's a minus sign here in each box. So I is for a particular box. And fresh water naturally will reduce the salinity, so there's a minus sign there. Right. Usually people make that, I have not made it because in my opinion, I don't see how you can put because there's so much salt on land, which is leaching into the ocean. How do you know whether it's conserved? Here, I'm not considering salinity conservation. I'm not explicitly put that constraint because if I were to put the constraint, I should know how much net salinity is there. I don't. And how do you take into account all the salt that's flowing from the land into the ocean? It's not coming back, definitely. So, which is why I just used this. Yeah. Which one? FI? FI, okay, freshwater flux due to precipitation evaporation. This is melting ice into the North Atlantic. The delta I1 is put because it's ice melts only into the North Atlantic, not into the other. So for I not equal to 1, my box I equal to 1 is my North Atlantic. I just copy pasted from my paper for ease of. So the contribution of melting ice only into the North Atlantic, contribution of melting or reforming ice only into the Southern Ocean, flow only into the North Atlantic of Amazon. So actually the Amazon flows just above the equator, empties just over the equator. It's around 2 to 10 degrees north of the equator. So you can safely say it's the North Atlantic. So if you were to put it into the South Atlantic, of course, behavior will change slightly. These I already told you. Actually, people measure these things. So it's an estimate, of course. People see how much water is flowing out at the mouth. So here you have to be careful. You have to look at multiple sources to be sure because you have a lot of misinformation also floating around. Right? Right. Right. Now we are taking care of flow. Now we come to the meat of the thing, carbon dioxide. Carbon dioxide content of the ocean is determined by the reversible chemical reaction of carbon dioxide that's dissolved into the ocean through exchange as well. And whatever carbon dioxide is coming in through the carbon, which is coming in through the flows. Now, when it's absorbed from the atmosphere, you have a mean gas transfer velocity, which is gamma I, which is dependent upon various things. We'll come and see to that later. AEI is, we are assuming that it's taking place over the surface of the ocean. So AI is the area of each box. So we have to plug in a number there. VI is the volume of that corresponding box. K0 is the solubility constant of CO2. How much of this will be dissolved in water? That's also a function of temperature and salinity and pressure. TCO2 is the partial pressure of carbon dioxide in air. And CI determines the aqueous carbon dioxide. This thing. So this is the change of CI due to absorption from the atmosphere. Okay. Now, what is the CI? This CI actually is this quantity here, CO2. How much of this is being actually dissolved? So there's a whole set of nasty equations. This is just a simplified version. The marine chemistry of carbon dioxide dissolution is a big mess. So, and not something I would even try to go into. But this is what, it's a simplified set of equations. Broadly, carbon dioxide gets dissolved into aqueous carbon dioxide in the water. This reacts with water to form carbonic acid. Carbonic acid dissociates to form hydrogen ions and bicarbonate ions. Bicarbonate again dissolves into hydrogen and carbonate. And these carbonate ions react with various minerals in the water, calcium, for example, which is the predominant thing, to form calcium carbonate, and that's how the reaction goes. Now, percentage-wise, bicarbonate and carbonate content dominate completely in terms of percentage-wise, around 80 to 90%. But, so any changes in 90 or 95% of this stuff, you can hardly make out. But the crucial thing that we are interested in is how much of it is actually dissolved. So we want to see how the small component in this whole carbon system, how can it be used as an indicator in understanding carbon sink formation? That's the logic we are using. Yes, or shells or water mollusks, which form calcium. Except that when the water becomes acidic, more carbon dioxide is absorbed, more carbonic acid is formed, it's no longer able to assimilate. The coral leaches. No, this is fine by itself, but it's a reversible reaction, right? So the more carbonic acid forms, this might form and dissolve. So that's a fine balance about how things go. But all of that is chemistry and not my cup of tea. Okay. So again, we are not replicating the full marine carbon cycle. It's a task beyond my ability. When we talk of this whole carbon pump sink, how carbon is being absorbed into the ocean, one thing we should just remember is there are various pumps, they call. One is the physical carbon pump, where carbon dioxide is absorbed from the atmosphere, dissolves, and then again goes out. Other is the biological carbon pump, where dissolved carbon dioxide reacts with organic matter and goes and gets stored. Okay, so here carbon storage is by sedimentation, as calcium carbonate. Here it is just carbon, aqueous carbon, which is stored in deep waters. In both cases, the oceans are acting as sinks. Right, so what we are trying to do is model on change how carbon dioxide, aqueous carbon dioxide is changing the ocean. And Ni denotes the content, the immediate contents, I'm not saying what, of those carbon, of the carbon reaction. And when I'm denoting this by Ci, the rest of this I'm just denoting by Ni. I'm not being particular about which species I'm denoting that by. Right. So we set up this set of equations. You have absorption from the atmosphere. You have carbonate coming in from the Amazon. You have this carbonate, which is dissociating into other quantities. The reversible reaction is also there. So Kc and Kn are the rate constants for the reversible reactions. Then you have carbonate being brought in by flows of the ocean, carbonates which are flowing out of the ocean. Similarly for N. Now, one thing we have to also take into account is that at deep seas, where pressures are different, temperatures are different, the carbonate content varies. It's a function of temperature and density. So you have to make a correction for that when you are taking into account deep sea content of carbon dioxide. That's right. So these, along with the equation, ordinary differential equation I showed you in the first earlier page for salinity, together we have 3 equations for 5 boxes. So you now have 15 coupled differential equations that you have to solve. Okay. Right. And we take the initial conditions from data, from naturally available data, freely available data for carbon dioxide vapor pressure for the year 2000 for every ocean. So when I say gridded data, we are trying to replicate what is seen naturally. So we're looking at 5 degrees by 5 degrees kind of grids in the ocean. And looking at the data there, also wind values and a lot of other things, which I'm not explaining here. So we can use the average PCO2 values for each ocean for the year 2000, and then start off with some initial values in order to solve these differential equations. Similarly, salinity values for each ocean for 2000 were taken as our initial value. Right. Now, when we talk of carbon dioxide in the atmosphere, there's something known as the Keeling curve, named after Charles Keeling. He was collecting data right from 1958 in Hawaii on how carbon dioxide varies in the atmosphere over the years. So you see this zigzag thing. This is because of seasonal oscillations where there's temperature variations in the atmosphere. So each zigzag would correspond to, say, a year. So what we have done is we use this Keeling curve as a measure to obtain temperature dependence as well as temporal dependence for fixing our PCO2 values. So this is what we did. We fitted a straight line to the Keeling curve, and we got this dependence where T is in months. And in order to actually see how temperature change is affecting carbon dioxide absorption, we are looking at also the functional dependence on time of the sea surface temperature for all these years. Yes, so this was taken in Hawaii. So the observatory is Mauna Loa Observatory. But it's assumed that since it's in the middle of the ocean, it's assumed that it can stand for the rest of the atmosphere. Not really, because the atmosphere is a circulating thing. It's not static. So on the whole, on average, it should work out. Right. Where? Sorry, where? This? Huh. This is CI prime, just for this. Yes. Yes, this is for deep sea flows alone. That T is constant. So T doesn't show up here, but it actually shows up in this guy, in K, in Q also it comes in. So it's implicitly sitting inside. So, right. So this again, we had to look at data for sea surface temperature variations in each ocean. Of course, you have seasonal oscillations. So we took a linear fit because we didn't know what else to do. And these were the expressions, how temperature in the 5 oceans, North Atlantic, North Atlantic, South Atlantic, Southern, Pacific, and Indian Ocean, how they vary with time. Okay, so now we have a measure of temperature variation with time for sea surface temperature. Right. Now we had something called, sorry, I had to go back and forth. You have this gas transfer velocity of how much carbon dioxide is being absorbed from the atmosphere into the ocean. That actually is a very nonlinear function of temperature. So you have to plug that in. Solubility of carbon dioxide in the water, again, is not a trivial function of temperature. So this was calculated at every iteration of when we are solving the differential equation. And for each instant of time, so you're able to find out CI, the values of carbon dioxide aqueous, Ni, and salinity of the oceans. Right, so that's how we did it for the first part. This is what we were getting. If you look at the temporal evolution of carbon dioxide, dissolved carbon dioxide, aqueous carbon dioxide, as a function of time, starting from 2000, this is what you see. The Southern Ocean is the maximum, has got the maximum content of carbon dioxide, is the major sink. This is also reflected in reality where the Southern Ocean has over 40% of carbon dioxide absorption of the oceans. Next is the South Atlantic, North Atlantic and South Atlantic. Here, this is actually depends upon where we take the boundaries of the North Atlantic and South Atlantic. I have a feeling I took it incorrectly. I didn't make it large enough, which is why the South Atlantic is predominant. Otherwise, the North Atlantic slightly pips South Atlantic as the larger carbon dioxide absorber amongst other oceans, followed by the Indian and the Pacific, which is also as a seen in real life. No, so, okay, this, I should make myself clear. So this, ours is a box model. So when I say carbon dioxide is the average value of each box. I'm not specifying the latitude or longitude in this case. So, and when I'm reporting this kind of number, this is all I'm going to do. Okay, but in spatial location, we'll come to that. Yes. 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 Cooler waters, of course, absorb more. They absorb more. Also, there's downwelling of the deeper ocean currents drag aqueous carbon dioxide more towards the southern ocean. That's it. Okay, and this. Not really, not so much. It's just that the currents flow is like that. But of course, that may determine the flow of current. So that indirectly, perhaps, but. Right. No, so these are predictions. If you'll notice, these are very minute. Well, if you look at it, look at the numbers. On the whole, if you have to look at the numbers themselves, they are not all that different. But yes, initially they are closer, but they are changing with time. And this is what is seen also. Southern Ocean is more and more absorbing carbon dioxide. Okay, now you'll wonder, of course, though I didn't, those of you who are wondering but keeping quiet, does this go indefinitely up, which cannot happen, obviously. So the drawback in the way we are calculating it is because since it all depends upon some initial conditions, beyond the time when things start to plateau out, you should, strictly speaking, recalculate using the next initial conditions so that the form of the curve gets recalibrated. If you were really, really interested in the actual values. We were just looking at the trends, so we haven't done that. And it's too much pain. Because obviously this can't keep going on till infinity, right? It's not an indefinite increase. Or should not be. Similarly, salinity, the North Atlantic is the most saline of all oceans as per our calculations, and this is also seen in nature. This is followed by the South Atlantic and Southern Oceans, Pacific. Indian Ocean is the least saline of the group. So again, gratifying that this is what is seen experimentally or practically. Okay. So we have got a set of differential equations. So we have a set of nonlinear differential equations. Next obvious question is, how stable are these? How do they evolve with time? So for that, you find out what the fixed point is. That is, you put well, dx by dt to 0 and to see what this is. And this is the 15 variable system. So you have 15 values. The first 5 correspond to carbon values, aqueous carbon, the next to the reactant value, and the next last 5 to the salinity values. That's how we set it up. And again, to find out stability, find out the eigenvalues. And you see all these eigenvalues. And lastly, you will notice that, one second, there are also a set of complex eigenvalues, complex conjugate. Minus 3.8, 3.08 10 to the power minus 4 plus 5.9, and 3.08 10 to the power minus 5. Set of complex conjugate values corresponding to the Southern Ocean and the South Atlantic Ocean. Okay, we'll come back to this. Now, when you look at all of these, you will see that when you're talking of these fixed points, we are essentially talking of the mean values of aqueous carbon dioxide, salinity, etc. in each box. So not at any particular latitude or longitude. And when you look at eigenvalues, you get a bit more idea about the stability, which is that the S5 eigenvalue, salinity corresponding to Indian Ocean, that is approximately 0. So the fixed point is essentially a bifurcation point where things can be going this way and that way. Salinity of the South Atlantic and the Southern Ocean, S2 and S3, are complex conjugate even though they are small. So you would expect oscillations to occur between the two. And that was our interpretation. And this matches with a known variability of something known as the South Atlantic Antarctic Intermediate Water, which is given the anagram AIW anagram. And this corresponds to salinity oscillations between the Southern Ocean and the South Atlantic. This happens over various timescales. You have interannual, multi-decadal, centennial timescales, but that's also one which has got a 330-year periodicity. The timescale we calculate is around 270 years, which is roughly of the same order. So we are reasonably confident that the way of looking at things is correct. Right. Okay. Next, you look at basins of attraction. How does the nonlinear system evolve? Since we are looking at the Southern Ocean, which is the major carbon dioxide sink, we would like to have a feel for the stability of the carbon dioxide in the Southern Ocean. So we have plotted it, Southern Ocean versus carbon dioxide versus salinity. And we see that, so you see this fixed point is somewhere here. See that the trajectories are asymmetrical in behavior. Negative values are, what is it? Negative values are sinks. Wait, I'll just tell you what it is. No, negative values are, sources in my notation. Negative values here are sources, carbon dioxide sources. This part is sink. This, you can see, does not behave identically to this. So over shorter time periods, this is time periods, okay? So this is the time, in months. This is a distance from the fixed point. For shorter time periods, things in the Southern Ocean are favored by trajectories nearer the fixed points. Longer time periods, the yellow parts, you see the trajectories which are farther from the 6 points are for sources. This was for the Southern Ocean. We did something similar for the North Atlantic and Indian Ocean, and you see that there's a symmetry in the basin of attraction, which indicates that there's a coupling between the North Atlantic and Indian Ocean, even though they are not contiguous to each other, okay? And we'll come back to that again. Right, that's taken care of what we got from the set of ordinary differential equations. Now, the locations of sinks and sources. Do they stay in one place or do they move around with time and space? So to do that, what we did was we had each box, right? So for each box, we looked at the flow of carbon dioxide from one side to the other by means of a material derivative. So a material derivative is something like this, where flow is determined by the velocity, right? So C is the average value in each box. This is what we solved earlier, the 15 coupled differential equations. Now, starting with from some initial point, how does this vary over each box, keeping boundary conditions fixed on either side? Okay. So the velocities we used here were for wind velocities for in each box. So for each 5 degrees by 5 degrees grid had to be considered for a particular month, of course. You had, so we took January of some year 2000 and proceeded. This is what we got. So these are calculations. These are not what is seen. What we saw, we put it here. Negative values are carbon sources, the darker shades, the black shades. Positive values are carbon sinks. This was for 2003. So if you solve it for several months, 2003, 2005, 7, and 11. So you can see all these are sinks, sources. These the white ones are sinks. Okay. Okay. How does it compare to what is seen experimentally? Well, not experimentally, what is observed in nature? This is what is observed in nature. The carbon sinks are these purple blue shades. And again, this is for the particular year. This is for 2000 February. And this, I believe, was for 2003, I think, January of 2003, the calculation that we have. No, this for a particular month, January. No, so what we do is we calculate average wind velocity. We use the average wind velocities. So this is measured on a daily basis, right? Winds over each part. So it's a painful work here to kind of average the wind velocities for each grid for each month. So we selected January because we had to select something. So this is for average values for 1 month in 1 year. So, oh yeah, sorry. This again, this is averaged over February of 2000.
Sure.
Measured. So this left side thing is the measured, the depiction of the average data for February of 2000. Measured. Okay.
Right.
You do have data there. So yeah, actually 5 by 5 is a very poor, so we actually averaged it for 5 by 5. Otherwise, there's no way of doing anything in this. So these are carbon sinks. These are carbon sources. So broadly, there's no way you can get a one-to-one match because it's a different month, a different year. And of course, it's a theoretical model which has ignored all possible details. We just thought of boxes, right? Despite that, we are able to capture broadly carbon sink formation here, for example, source formation here, sink formation. This is the canary current somewhere here. This blue stream that you see. Okay. You're able to see this kind of thing. But capture something of what is observed in nature, even though, of course, you can not pretend that it's capturing the real thing. No, these are actually, green is around 0. Okay, so these are sources. Oh, in green, okay, if it's green, it means as much is released as is absorbed in those areas when you measure it. Again, those are functions of local temperature, density, salinity. It's all flowing, right? So, yeah, so you can't, which is why it's, yeah, it's a terrible thing to calculate. Anyway, so this is what we see theoretically from our equations using our material of convective derivatives for each box. Right. Okay. We have talked of what we see this. Okay. What can we say of the past? So when you talk of geological timescales, there are a whole set of, the terminology is very confusing. You have eons, which are long periods. Under them, you have eras, then you have periods, then you have epochs, then you have ages. And different people do it in different ways. Means you have 2-3 conventions. We are talking of the Miocene age, epoch, which is somewhere here, which was around 5.33 to 23 million years ago, which was known from the geological record to be a period of climatic change. So in terms of epoch, we are somewhere here. Man is here, the age of man, somewhere here, quaternary period. Miocene is sitting here at the boundary, just after the tertiary period, somewhere here. And we have all heard of Jurassic and Cretaceous period, that is much earlier, somewhere here. Okay. Why are we doing this? Because this goes, I talked of serendipity in choosing chemostat, and I also talked of having a hunch that the Amazon was important control parameter. Now, it so happened that somewhere there was, I came across an article which talked of geological changes in the Miocene period. So now the question was if they have, which caused formation of Andes. Now, if Andes are being formed and Amazon is flowing in the southern, in South America, surely the flow of the river would also have changed. If so, surely that would have had climatic effects. And you already see in other literature that the Miocene had major climatic changes. So the question, that the hunch was, is the Amazon acting as a control parameter for this whole system by flowing elsewhere? So what we did was, instead of allowing Amazon to flow into the North Atlantic, we put that to 0 and change the equation so that it flew into the Pacific. Okay. Now how do we quantify the amount of Amazon that's flowing into the Pacific millions of years ago? We have no clue, no handle, nothing. So we plucked a number out of thin air, 50 times the current flow. Okay, because we don't know. And then saw we get some nice effects. We do. Okay, but of course, it is, you don't know the numbers, but you know the effect. Let's put it that way. Okay, so we are interested, therefore, in this Miocene era. And we again looked in the literature. And as so often happens, various people do the same thing at similar times, right? So we came across, okay, this was what we were doing. Can you capture some of this? Okay, we came across one work by Russell Mapes in some obscure, well, obscure for us, Geological Society of America abstracts. Okay, you can't get the full text, but you can get the popular versions of these. During the Cretaceous periods, he tells us that the Amazon drained into the Pacific Ocean. Okay, how does he find out this? By looking at the mineral content that is seen east. So minerals that are found here or here, for example, are not what are found locally. They're found in the other part of the continent. So going back to the geological record, you had something known as the porous arch. This was still present, okay? The idea is that during the Miocene era, due to geological changes, Andes grew, and there's a body of water here, which was draining out. And due to the growth of the Andes, these guys got trapped between the water got trapped between the porous arch and the Andes, and then it started flowing eastward, into the Atlantic, as in the current day. So this was a nice thing that someone else is saying that you can have a nice, well, you get it. Right. So this is what we did. 50 times we got the Amazon to flow into the Pacific, shutting off the Atlantic flow. Thin air, I don't know. So I'll show you, because the quantity, we also did it for 100 and something else, but it's difficult to recalculate the whole thing. So just as we took one number and showed we have this effect, and we made a generic statement. Of course, it depends upon the number, because I don't know.
How do we even imagine that it would be more than this?
Why? Okay. We are trying to telescope the effect of millions of years into a short time, right? So even if the flow was less, it has been flowing and flowing and flowing for God knows how many hundreds of million years before. So, okay, I don't know. So, okay, let me take this huge thing, dump it in one go. That was the logic. Right. So this is for 2011 numbers. And again, I had no clue about salinity and wind patterns in millions of years ago. So I use the same numbers as today. So the only difference between this and this is that Amazon is now flowing 50 times more into the Pacific. That's the only difference. Okay, what do you see? You see different patterns. You see sinks which are absent. A source has become a sink. A sink has become a source. This was is in the Andaman Sea. Likewise, you see off Borneo, you see a source has become a sink. It has switched. You see the pattern, right? I don't know. I'm assuming that they were still growing, but I have no clue. This was at a time when the continent formation, the land masses had separated. That if I go further, then I can't say anything, because the oceans are no longer recognizable as today's oceans, which is why it's foolhardy to go before the Miocene. Because before the Miocene and Cretaceous periods, the land masses, they also, beyond period of time, you are not too sure about. For example, around Miocene and Cretaceous period, the Mediterranean was cut off from the Atlantic. Before that, it wasn't. It was kind of linked. So where you put the cutoff also matters.
Because it is said that Himalayas are continuous.
Right. Yeah. But I'm not really, for this problem, I don't know. I'm assuming they were still rising. But since they don't affect my oceans, I'm ignoring them. I think Himalayas are younger. Himalayas are youngest. Okay. I don't know. I think it's primarily rainfall, but I don't know because you do have snow in the Andes.
Yeah.
But I don't know what's the main source. I really don't know.
I mean, the rain, when the mountain is there, you will have two regions, right?
No, but the point is whether that's a glacier kind of thing. I think that's your question, right?
Yeah.
I don't think that's a glacier in the Andes, but
For that question, I have one.
huh.
If there is a mountain, then there will be a region where the clouds are stopped.
The rain shadow area, and then right.
The rain shadow.
Right.
So how was the Andes? Oh, sorry, what was the situation of Andes? That was
No. So see. Okay. Again, I'm going in the wrong direction. Please. Right. So this thing here. Around this time, the Andes hadn't really formed. See, in this Cretaceous area, there's supposed to have been a big lake kind of water body. I don't know how it was fed. Presumably from this side, water mountains were there on this side. I don't know. But presumably that's what you're asking, right?
Yeah.
Right.
How was this side the rain and the other side the rain shadow?
Perhaps, I don't know. No. The 50 times number was just to quantify the millions of years of flow on the other side. That's all. I'm making no statement whatsoever about the precipitation. This is just to quantify all that has happened before into a short time. Otherwise, I don't know how to quantify it. Right. So you see this striking changes. Namely, you have redistribution of carbon dioxide in the Pacific Ocean. This is redistributed. You have reduction in carbon dioxide absorption in the Southern Atlantic. You have increase of a band of carbon dioxide absorption size in the North Atlantic Ocean. Right here, the Canary Currents. Then there's a change of prominent sources which turn into sinks and vice versa in the south, in the Andaman Sea, off Borneo, also off Sydney. Okay, interestingly, this thing about temperature changes in the Andaman Sea in the Miocene period is also there in the literature. So this is one more thing for saying that the way we are thinking is correct, even though quantitatively, of course, we might be off completely. Qualitatively, we're doing it fine. Other thing that we see is effects on Antarctica and the Southern Ocean. You see that you have prominent carbon sink formation in Sulzberger, Rabbits, and Gitz ice shelves. This is this here, this region here, that corresponds to this region here. So this is the Antarctic Peninsula. This projection that you see, that's the Antarctic Peninsula. This thing. Okay. Then you have carbon sink changing into sources of the Verde and Larsen ice shelves, right here. That is here. You see, sink has become source. Then you have other enhanced carbon dioxide absorption in the Southern Ocean, east of the Antarctic Peninsula. And also on what is known as the Fimbul ice shelf and Western ice shelf, West ice shelf, which is on the east. Okay. So that corresponds to, where is this? This part. Okay. All of this, I'm showing you this because again, this matches with what is seen in the Miocene record. You also saw in the Miocene that you had this West Antarctic ice shelf that was formed in the upper tertiary period. So that again is what we see here. The other thing that we see, which I forgot to mention, is you have a cooler climate in Western Europe in the Miocene area because you have sinks forming, which means carbon dioxide is being absorbed by the ocean. So lesser carbon dioxide over the land, which means less heating of the atmosphere over the land, so cooler temperatures. This again is known. Later Miocene, you had a cooler Western Europe climate. India, unfortunately, people don't say anything. No one says anything in the literature. Andaman Sea, we know. Andaman Sea, it was cooler during the Miocene. You see, again, a white spot, a sink. Current day, you see a source. So that's a switching of sink and source here. So this, again, this matches nicely. But Indian subcontinent by itself, I don't know. Okay, about the number, about 50. If I take 50, there should be some justification or at least some quantification of what the number does, right? So this is the normal flow salinity in the, as an example, Pacific Ocean, salinity for normal flow, 50 times the normal flow, 100 times the normal flow. How it changes. By normal flow, I mean Amazon into the Pacific. Okay. So current day, the estimated Miocene number that we had taken, and if you increase it, this is what would happen. Okay. Okay, that's A. And similarly, these are what would happen for. This is what would happen if this is what is in current day. This is for carbon dioxide. This is what would happen if you took 50 times the flow into the Amazon, of Amazon into the Pacific. So Southern Ocean is still there, but now South Atlantic is no longer the dominant one next. It's now the Pacific. And if you keep increasing the flow, carbon content in the Pacific becomes the predominant thing. Right, this is what, so if you want to know what happens when you change the number, this is what will happen. I don't know which is the correct thing. But what we took seems to match somehow fortuitously. Right, so these are our principal features and findings. We are able to capture spatial temporal evolution of carbon sinks and sources in the various oceans. We have shown how freshwater flow is a crucial control parameter in this whole ocean system and can crucially affect global climate patterns. And this hopefully can be used for modeling the climates or geological epochs when we have no clue about what's happening in those times. We see that a coupling in the North Atlantic getting, okay, this I forgot to show you. I should show you. Always. Right. So I didn't make it clear enough, but this is what I wanted to say. When you have flow into the Atlantic, see, when flow is being restricted of fresh water into the Atlantic, you have changes here, but you have, again, changes here in the Indian Ocean, which is not a contiguous body of water. And we also saw from the basin of attraction that that's a symmetric diagram when you plot carbon dioxide for Atlantic, North Atlantic and Indian Ocean. So there's a coupling there, which is inherent in the system of equations. So when we make this kind of simplified model, cause and effect shows up, which we won't see if you look at global climate models where you look at all the possible numbers, all the data, because you're lost in the data and such things. So a simplified model like this has that advantage that you can identify possible effects, cause and effects in the global climate system. So we looked at, we predicted, we find the South Atlantic, Antarctic intermediate water variability, because we saw you had a couple of complex conjugate eigenvalues for Southern and South Atlantic Ocean salinities. And broadly, these things seem to be in agreement with what's reported in the literature. Yeah, thanks.
Was there any assumptions about the way the flows work?
No.
Something stable there or no?
We didn't do stability analysis for modified system because too much work, broadly. The only other assumption made is, see, correct, we have assumed same values for salinity, carbon dioxide, not carbon dioxide, PCO2, carbon dioxide vapor pressure. Yes, those we have assumed as in current day. Flow rates, everything else current day. The only thing we changed is the Amazon volume flow. That's all. Because we didn't change any of the others because we have no clue of what the values were.
The related question is, when you assume the water is flowing to the Pacific,
Yes.
then it's very close to the equator, right? So
In the Atlantic, yes. In the Atlantic, this is around 10, I think 5 to 10 degrees. Very close to the equator.
So my question was simply that things could have been a little, I mean, if we did an analysis where it flows a little southward,
yes,
versus a little northward,
yes,
do you have any idea whether that makes a difference to the observation? Or
it will, because when you look at, 1 second, let me go back. Right. Now, it will, I know, because here I see that carbon dioxide in Southern Atlantic shows to be slightly more than North Atlantic, right? This is what is seen. But for practically, it is known that North Atlantic, at least in some measurements, is slightly more than South Atlantic. So where I took the boundaries of my ocean mattered crucially, right? So yes, if you have flow into the South Atlantic, yes, things will change. But since this flow is essentially changing the salinity of the of the Pacific Ocean and the North Atlantic.
Since it's the Pacific, it doesn't affect this side. That's the problem. So the Pacific is taken as one form.
Yes, and you'll notice one more thing, which I didn't explicitly say. 1 second, please. There's no inflow of surface currents into the Pacific. That's one difference of the Pacific from the other oceans. All the other oceans have inflow of surface currents. Pacific doesn't have that. So Pacific Ocean by itself is a kind of outlier, even if you look at the temperature oscillations. Right. Pacific. You can straight away see the behavior is slightly different. If you look at the way things are evolving with time. So my gut feeling is that broadly the behavior that we have predicted will persist, except that the magnitudes will change. That's my feeling. And if it changes too much, of course, that's the point. North Atlantic and Indian Ocean are coupled. So if it changes too much, then we'll see changes even in the Indian Ocean. That point is there. Correct.
Why we didn't segment the Pacific, South Atlantic, North Atlantic, and Pacific is much larger.
Yes, but it's one body of water. So there's no, if you split it, you don't get anything. There's no other flow that's occurring. It's just one box. Yes, correct. Which one?
The 330 years periodicity or something that you said.
That's from current day. Yeah.
So, but what does it mean? It means that everything starts getting recalculated from there?
No, the 330-year thing means that, see, we got that from the inverse of the eigenvalues that we calculated.
Correct, yeah,
for so that's the time period of oscillation between the South Atlantic and the Southern. At least the time period that stands out in this kind of model.
This is the slowest eigenvalue.
Not necessarily, you have others also. Multi-centennial timescales are there. But this is one thing which seems to match. This is what we get, and fortunately this...
So every 300 years, something becomes a sink and something becomes a source.
No, that was for salinity oscillations, not the carbon oscillations. There's no carbon dioxide oscillation between South Atlantic and Southern, but the magnitude of salinity in the Southern and South Atlantic varies over a period of time.
That's what the 330 years is.
Correct.
Correct. So this graph, the green graph, then that's salinity, no?
That is salinity, the right side one.
So it should again go back to 34.5 and then the cycle should start.
Hold on, except that this is in months, not years. So like I said, see, even here, I stopped here because I'm not confident beyond this point. Can't keep going. Here, I should strictly speaking, recalibrate my initial conditions, recalculate, again generate. So this is fine for a limited 250, 200 months, 5 years, 10 years, 20 years. But beyond that, it's a question mark. But the point is, it's a simple box model. You don't, a humongous amount of things are happening in the ocean which you have just ignored, and you're still getting useful data. That's the point.
Any climate change interventions can be designed from this kind of models?
I'm afraid to say anything because unless if you do a good job, yes. If you have a person saying that every say 100 months sit and recalculate, then yes, you can make some predictions. Then yes, definitely. But yeah, you have to do it very carefully because it's too simple a model to actually capture everything.
We should block the other Amazon which I don't have.
Yeah.
The Amazon material. Thank you.
Thanks.